In this video, we discuss another way to polarize light, which is polarization by reflection. It turns out that when the angle between the reflected ray and the refracted ray is 90 degrees, then the reflected ray is polarized perpendicular to the plane of incidence. Why is that? You don't need to know why in Physics 9b, but if you're curious, I will give you the short explanation. In fact, when light arrives to a material, it is absorbed and re-emitted by atoms. And the way this works is that the electric field of the light, when absorbed, will create an oscillating electric dipole. So it will separate the center of the positive charges from the center of the negative charges of the atom. And then this oscillating dipole will re-radiate light and create the reflected and the refracted ray of light. But there is no radiation in the direction of the dipole moment. And this is because light is a transverse wave of electric and magnetic field. So the electric field has to be perpendicular to the propagation direction. And so when the refracted ray is perpendicular to the reflected ray, then the component of the light with an electric field that is in the plane of incidence will not be reflected. And only the component of the light with an electric field that is perpendicular to the plane of incidence will be reflected. And so the reflected light is polarized perpendicular to the plane of incidence. Now we will show that this polarizing angle is given by a tangent theta p is equal to nb over na, where theta p is the polarizing angle. And if you look at the figure, it is the angle between the incident light and the normal to the reflecting surface. And Na and Nb are the refraction indices of the two materials at the interface. Now, sometimes the polarizing angle is also called the Brewster angle, and it is written also as theta b with uppercase B. In that case, make sure you don't confuse theta Brewster with theta b with a lowercase b, which is the angle of the refracted ray from the normal to the surface. Now, to show this relation, we can start by writing Snell's law, right? Which is Na sine theta A is equal to Nb sine theta B. Now, in this situation, theta A will be equal to theta P. And theta B, if you look at the figure, it will be equal to 180 degrees minus theta P minus 90 degrees. And so theta B is equal to 90 degrees minus theta P. So Snell's law becomes Na sine theta P is equal to Nb sine 90 degrees minus theta P. And this is equal to cosine theta P. And so tangent theta P, which is equal to sine theta P over cosine theta P, will be equal to Nb over Na, right? So we obtain the relation for the polarizing angle simply using Snell's law, in fact. Now, in the previous video, we mentioned that some types of sunglasses are polarized. In fact, the polarizing axis is chosen to be vertical. And why is that? Well, mostly, in fact, because the Earth is flat. I'm kidding, of course. The Earth is not flat, but to our scale, right, because we're small, for us, the ground is horizontal. And so when the sun is high in the sky, then the sunlight that is reflected on the horizontal floor is polarized horizontally. And so sunglasses have their polarizing axis vertical to reduce the reflected light. And so the natural light that is directly coming from the sun can get through because it contains some component that is polarized vertically, but the reflected light is mostly absorbed because it is mostly polarized horizontally. And we can see that easily. In fact, I'm going to demonstrate this right now. So I can create some reflected light where you have, just simply going to take this light here. I'm going to create so you can see the reflected light on the floor. And now if I take polarized glasses, now you can see that the reflected light is removed. And if I rotate those glasses, then it gets through, right? So rotate again. So you can see that the reflected light on the floor here is indeed polarized. And we almost suppress it completely, so we're almost very close to the Brewster angle by chance. So in fact, it's pretty fun to look at this, all the light that is around you that is polarized. Look at this, for example, light that is reflected on the windshields of cars. You can see that the reflected light is polarized and can be reduced by a lot, actually, when you are using a polarizer.